Hi everyone, and welcome to the first of 4 videos going through some past exam questions on the topic of acids and Ka. So this first question here, we've got lots of information about different acids, formulas, pKa values and all sorts. But it starts off nice and easy. What is meant by a Bronsted-Lowry acid? A Bronsted-Lowry acid is a proton donor. That's just a 1-mark definition that you need to learn. What is meant by the strength of an acid? Well, these are all weak acids. Okay. Doesn't actually tell us that, but we can tell the fact that we're talking about Ka values and this sort of thing means they're going to be weak acids. Remember, weak acids only partly dissociate. So the strength of the acid is, well, what do we mean by partly? Okay, how much does it dissociate? The stronger it is, the more it dissociates. Okay, so the strength of the acid is essentially the extent to which it dissociates. Or you could use the word ionizes instead of dissociates if you're more comfortable using that. It's the same thing. So therefore, include an equation for one of these acids. Okay, we'll just use the first one. So we'll take our benzoic acid. So the fact that it's a weak acid means it partly dissociates. So the important thing here is that we write it with an equilibrium sign. So here is our benzoic acid. It's going to dissociate, but it's only going to partly dissociate. We must have that equilibrium sign. And we're going to end up with the conjugate base as the negative ion, and then there's the H+ ion that it's giving away. Right, it then says place the acids in this table in order of increasing strength. So here we need to be careful. Okay, the thing that tells us the strength of the acid is the Ka value. Remember, the Ka is just the equilibrium constant for this equilibrium. Equilibrium constants, remember, are products over reactants. So if I've got a big value for my Ka, it means I've got lots of products and not many reactants, which means my acid has dissociated quite a lot. Okay, so what we're looking for with the strength of the acid, okay, a stronger acid means it's going to have a higher Ka value. Yeah, because it's going to dissociate more. I'm going to get more of this. I'm going to have a bigger value for the equilibrium constant. But annoyingly, in the table, they haven't given us Ka values, they've given us the pKa values. Okay. Well, remember that pKa is the negative log of the Ka. Okay, remember anything with a little p in front. If it's an acids question, if it's got a little p in front of it, it means you're taking the negative log. pH, pKa, all means it's got a little p, it means it's a negative log. So if I'm doing the negative log of the Ka, then the pattern's going to be the other way around because it's negative. Okay, so a stronger acid is going to have a lower pKa. Higher Ka, but lower pKa because of this negative log. So we're looking for the order of strength. So the strongest acid is going to have the lowest pKa. So out of these, the lowest pKa we've got is this one, so pyruvic acid. So that is going to be the strongest one. Be careful here, we get this the right way around. Then it's going to be the lactic acid, then the benzoic acid, and finally our acetic acid is going to be the weakest because it's got the highest pKa. Right, then we can actually put this to use then, because now they're saying, okay, if I react benzoic acid and lactic acid together, what's going to happen? This is the acid-base pairs idea. It's not asking us to actually label the acid-base pairs here, it just wants us to say what the products are going to be. So because of what we've said here, we've said that the lactic acid is the stronger one of the two, okay, because it's got that lower pKa. So the lactic acid here is this one. So if this is the stronger acid, it's going to be a proton donor, and it's going to donate its proton to the benzoic acid. So the benzoic acid is going to end up with an extra proton. So there's my benzoic acid, but now if I've gained another proton, it's going to be H2 with a positive charge. I know it looks a bit weird, but that would be how you'd write it. And then the lactic acid is going to have lost its proton, it's going to donate it. So we're just going to have this as the conjugate base, just copy it carefully. and that's giving away its proton. Do remember to put the charges on. Okay. If we carry on with this sort of question, then we're still talking about the same types of acid, so it's asking us about our pyruvic acid again, and it's reacting with calcium hydroxide. It wants us to write an equation for that. So our pyruvic acid, if we go back and find it here, so here's the formula, CH3CO COOH. Okay, so CH3CO COOH. So there's our pyruvic acid. If we're reacting it with calcium hydroxide, calcium is group 2, isn't it? So calcium hydroxide is going to have that formula. It's therefore going to make, well, the acid is going to donate its protons. That's what it does. And we're going to make the salt of the acid, the calcium salt. So I'm going to end up with calcium and then 2 of the negative ion from the acid. So I'm going to end up with 2 of that. So therefore I must have started with 2 of these to balance it. And then the H plus is going to get donated to the OH minus. That's going to happen twice. So I'm going to get 2 water molecules. Okay, if we then want to write an ionic equation for this, and remember ionic equations, what we do is anything that's an aqueous solution, we will write it as separate ions. So we've got aqueous pyruvic acid, we've got aqueous calcium hydroxide, right? It's good, they will tell you whether things are in a solution or not. They don't tell you about the product, but salts are always soluble. Okay. So what's going to happen here then is, this is going to split up into the negative ion, the conjugate base of the acid, and an H plus ion. But I'm going to have these negative ions here, and I'm also going to have those negative ions there. So they're going to cancel out. That ion and that ion are going to cancel out. I'm going to get H plus ions here. I've got calcium ions and hydroxide ions. Well, the calcium ions are also going to cancel out. So I'm just going to be left with H plus ions, OH minus ions, and water molecules. Okay. So I'm going to 2 H plus ions from there, 2 OH minus ions from here, and I'm going to end up with 2 H2O. Actually, I didn't need to write the 2's here. I could just cancel the 2's out, can I? That would be fine. But you could leave it like that. There's no problem with that, as long as it's in the right ratio. So it's that idea of we cancelling out the spectator ions, right? The ions from the acid and the calcium ions are just sitting there. This is the actual change. This is the neutralisation, isn't it? This is the ionic equation for neutralisation. Right, then we get to doing a calculation. The pH of an acid can be calculated from its pKa value. Calculate the pH of a solution of pyruvic acid. Okay. Anytime we get calculations, the first thing we're going to do is write out our expression for Ka. Okay, we're doing pyruvic acid, so it's still the same acid, so it's this acid here. So Ka is going to be the H plus concentration times the times the A minus, which is the negative ion from the acid, over the acid concentration. It's always a good idea to actually write this out with the formula rather than just having A minus and HA. They don't usually give you a mark for that. They want you to put the actual formulas in. So if that's our Ka expression, we want to calculate the pH. Okay, so we're gonna want to know the H plus concentration, because then we can go from the H plus concentration to the pH. Okay. To do that, we have to do a little trick where we say that these two concentrations are going to be equal to each other. Okay, because it's a weak acid, when the acid dissociates, one molecule of the acid will make one H plus ion and one A minus ion. Okay. So the acids can dissociate and make one of each of these. So these two concentrations will always be equal. Okay. So therefore we can change this into H plus squared. And now we can start rearranging this to get the one we want. So the H plus squared is going to be equal to the Ka times the acid concentration. And therefore the H plus concentration is going to be equal to the square root of this calculation. Right, so now we can just substitute our numbers in. We know Ka, no, we don't know our Ka value because we've been given the pKa. So that's the first thing we need to do, is turn the pKa into the Ka. Okay. So we said that the pKa is the negative log of the Ka. So therefore, Ka is 10 to the power of minus the pKa. So in this case, Ka is going to be 10 to the power of minus, we go back to our data, what is it? Pyruvic acid. So we need to go back. Pyruvic acid, its pK is 2.39. So the Ka is going to be 10 to the power of minus 2.39. And the concentration they've given us here. Okay. So the H plus concentration, therefore, is going to be the square root of 10 to the power of minus 2.39 times 0.015. Right, let's work this out. 10 to the minus 2.39 times that by 0.015. So we've got that. Oh, and then I need to do the square root of it, don't I? Square root of that. So we end up with 7.82 times 10 to the minus 3. So that is our H plus concentration. And then remember, to get the pH from the H plus concentration, we do the negative log. Yeah, so we're saying that the pH is the negative log of the H plus concentration. So therefore, the pH is the negative log of 7.82 times 10 to the minus 3. So we're just going to take the log of that. And I've got minus 2.1, but I haven't done the negative log, right? So if I do the negative, we need to take away the minus sign. So we get a pH of 2.1, does it say? Yeah, 2 decimal places, so 2.11 we're going to get. Is that a reasonable pH for a weak acid? Yeah, that's what we're expecting, isn't it? It's below 7, but it's not particularly low. It's not pH 1 or something. So that seems reasonable. Right, last couple of questions we've got here. Here we've got the acid-base pairs again. So we've got this Cn minus ion. In aqueous solution, Cn minus, equilibrium is set up, complete the equation. Okay, so here, well, it must be the water that's acting as the acid. That's the only thing that's got a proton to donate. It hasn't got any H plus ions that it can donate. So that's going to give it to that. So we're going to end up making HCN and OH minus. And therefore the water has been the acid, and this has been the base. And then on this side, the OH minus is definitely the base, isn't it? And this must be the acid. So then let's call that acid 1, and that must be acid 2. And if that water is acid 1, then the OH minus is base 1, isn't it? Because these are the two that are a conjugate acid-base pair. And then this must be base 2, because these two are a conjugate acid-base pair. Okay, remember the difference in that conjugate pair is just the H plus ion. There's an H plus difference between those two, and there's an H plus difference between those two. Okay, you should always have an acid and a base on each side, and you should have a number 1 and a number 2 on each side. Okay, you could swap all the numbers around. I could have 1, 2, 1, 2. That would be fine, as long as you've paired up the right two with the same number. Explain in terms of equilibrium why acidic conditions should not be used. Well, the problem here is it's if we go back to what it's told us, it says this is the conjugate base of a very toxic acid. Well, what we've shown is that if we use acidic conditions, we can end up making that very toxic weak acid, aren't we? So that's the problem. Okay. So in terms of equilibrium, acidic conditions means we've got more H plus ions, right? So that's going to shift the equilibrium to the right. Okay, we're going to add the H plus ions to this and make this. So acidic conditions would shift the equilibrium to the right. Just be careful when you're looking at these questions and try and answer them exactly. Even if it's saying in terms of equilibrium, put the word equilibrium in your answer, then you're more likely to get a mark. We shift the equilibrium to the right, forming HCN, which it told us is toxic. So that's why it's not a good idea.